Okay, so today I want to get into small signal analysis. But before we do that, there was one slide that needed to be covered. That was about early voltage in BJT, chapter for BJT. So let's look at that first. So early effect in early voltage. So if you try to use BJT, like say early in the morning, like 2 or 3 o'clock in the morning, you see, I couldn't even go through the sentence. How many of you read through the book about the early effect? Okay. And nothing to do with the time. It was a effect that was discovered by a scientist who was working at Bell Labs. Name was James Early. As at least I think I got his first name correct. Um, and he discovered that when you took the characteristic output curves of a BJT and extrapolated them into the second quadrant all the way back negative, they all converged at one point. And that voltage came to be named after him, and the effect that he discovered was named after him, hence early effect and early voltage. Okay. Um, on the output characteristic, we like to state that they are flat lines, right? So we said as VCE increases, IC remains constant. Was this truly the case when you obtain your characteristic curves? Or was there a slight increase? Slight increase. Generally assumed constant, I would say. There's a lot of assumptions and approximations in semiconductor analysis. Okay, so this is VCE and this is IC. And so we say that the BJT functions as a constant current source. But that's not really true. There is a slight curve, right? So there is a curve. Those curves are somewhat, and this is going to be exaggerated. Actually, why am I drawing it? We have it here. So let's see. Okay. All right. So as I was saying, we have VCE on the x-axis, and you have IC on the y-axis. Collector current, collector emitter voltage. And if you take and extrapolate these plots, along with the curve that they make in the first quadrant, extrapolate it back onto the negative side, then they all merge at a single point. That single point is labeled as VA, the early voltage. Okay. It's typically not at minus 15. This minus 15 is exaggerated. It's typically like hundreds of volts. This is not something, at least there isn't a method that I know where we can actually physically measure this. Okay. This is a theoretical, this is basically a theory. And the reason it happens, we'll look at semiconductor physics for a bit. Let's see how and why this happens. Okay. What is actually happening here is we have a BJT, we forward bias the emitter base junction. So emitter base junction is forward bias. And then you have the collector base junction that is reverse bias. Well, what happens when you reverse bias a PN junction? The depletion region increases. So if the depletion region is increasing, is increasing in both directions, right? So depletion region increases on both directions. So it's now encroaching into the base as well as the collector. The collector is not so much of a problem because it's, well, first of all, it's lightly doped. Plus, it is the largest of all the regions in the BJT. The base, on the other hand, is the smallest or the thinnest region with very little doping, like the least, one of the least doping amongst the three. And so if the depletion region in the base area is increasing, the effective base width decreases. So this is obviously not to scale, but the width of the base decreases. And because the width is decreasing, now there are changes in the performance of the BJT. Okay, performance of the BJT. The result, or not the result, the effect is that the base width decreases and the early voltage, sorry, I'm burbling or mixing up my words. The effect of increasing VCE is that is increasingly reverse biasing the collector base junction. And because of the increasing reverse bias, the depletion region is increasing. Because the depletion region is increasing, the base width is effectively decreasing. And what that does is it lowers the output resist or lowers the resistance or lowers the effective resistance at the output of the BJT. And because it lowers the effective resistance, now your collector current is increasing. And that's why we have a slope as VCE increases. So IC increases. And because IC increases, effective resistance is decreasing. Right? Remember, the fundamental operation is that the charge carriers come from the emitter, go into the base, and in the base, you have a certain amount of electron hole recombination that occurs, flows out as base current, and the remaining cross over into the collector. Now, if the base region is decreased, well, instead of flowing out of the base terminal, more and more charge carriers are now going into the collector, right? And so the collector current effectively increases, base current kind of decreases, and we say effective output resistance is also decreasing. And this kind of places an upper limit on the amplifier performance. So if you're using BJT as an amplifier, that puts an upper limit on the performance of a BJT amplifier. And that's why the early effect and early voltage are taken into account when you're designing a BJT. Okay, that's what the early effect is. All right. Right. Any questions? Okay. All right. Let's go to chapter 7, and I want to take just a small pause here because we rushed through this at the end of last class on Friday. Just wanted to make sure that everybody understands this and I answer any questions before we move on. Did you all review this at all? I'm going to ask this on the final exam. Possibly. Load line analysis and this graphical analysis is a very, I found over the years, it's a very good method to explain how and why it amplifies. or how and why it works as an amplifier. It explains amplification. It also explains inversion. And it explains the DC offset. Okay. All right. Let's talk about capacitors. All right. So if you, not if you, I think almost everyone is done with Lab 8, right? Is anyone yet to do Lab 8 this week? Yes. You have Lab 8 this week? Okay. Interesting. Anyway, so we use capacitors in our circuits, both on the input side as well as the output side. Depending on the purpose, we call them either bypass capacitors or we call them coupling capacitors. Sometimes they are functions could be the same. I mean, both functions could be performed by the same capacitor. So if you have a capacitor on the input side, what is the property of a capacitor when it comes to DC? Zero. What does it do to DC signals? EE211, DC steady state, capacitor gets fully charged, behaves like an open circuit. So we say it blocks the DC. Higher the frequency, the more current that flows through it because it's constantly switching. And so for an AC signal, it behaves like a short circuit. For a DC, it behaves like an open circuit. So it behaves like infinite or open resistance for DC, meaning it blocks the DC and it allows the AC to pass through. So it couples the AC signal into the base, so to speak. So we call that as coupling capacitor. So capacitor has filtering properties. Right? Blocks DC and allows AC. Well, of course, depending on the frequencies. So on the input side, we have a capacitor C1, and the C1 capacitor is going to appear as an open circuit or infinite resistance to DC signals. At the same time, it has very low reactance to AC and behaves like a short circuit for AC signals. This, of course, also depends on the frequency of your input signals, and so you choose the value for capacitors accordingly. Okay. On the output side, again, we are using capacitor C2 and the same purpose as C1. In Lab 8, we didn't do that. In Lab 8, we did not use a capacitor at the output. We use a capacitor on the input side. We do not use a capacitor at the output. So if you notice, there was a DC offset at with your outputs in Lab 8. Okay. If you want to block it, we either use a negative clamper or we can try and use a capacitor. Both methods have their pros and cons. What about C3? What do you think C3 is doing? We didn't have C3 in Lab 8 either. Couldn't hear. It's filtering, yes. So what it's doing is, well, what is the purpose of these two resistors? It's a biasing, right? It's a voltage divider network, creates a bias. Bias means it's fixing our DC operating point in the middle of the active region, or in the middle of wherever we want it to function. So if current's flowing through here, right, is going to be fixed. But if an AC signal arrives, it's going to change the bias. So we don't want any AC current flowing through here to affect our DC bias. And so C3 is used as a bypass capacitor. It blocks the DC, so it doesn't affect the bias point. Plus, it allows a pathway for the AC to flow through directly to ground, so it does not affect the biasing circuit. And so let's say blocks DC and allows the AC to pass through and not affect the DC bias point. Okay. The C1 and C2 are coupling capacitors, and C3 would be known as a bypass capacitor. It's also sometimes referred to as emitter bypass capacitor. Okay. All right, questions? Yes. I over P slash I slash P input, O slash P output. It's my shorthand acronym. Okay. So when we analyze these kind of circuits where you have both AC and DC signals present, we separate out the analysis. We analyze the circuit separately for DC, and we analyze the circuit separately for AC. Thus, we obtain DC values for our DC sources and bias points, and then we analyze it separately for AC. So AC is typically known as small signal analysis. So for DC analysis, what we do is, well, we replace capacitors with their DC equivalents. So for a DC equivalent, capacitor is an open circuit. So if we separate out the open circuit, let's see if today works without sending a message. All right, if we separate that out, that means that the input side is no longer connected here and here. The output side is disconnected. So all that remains, if you're trying to analyze for DC, is simply the 4 resistors and the transistor. Okay, this is a voltage divider bias. So voltage divider bias circuit from R1 and R2. And for DC analysis, we replace all inductors and capacitors in the circuit with their DC steady state representation. Or DC steady state equivalents. Capacitors are replaced with an open circuit, and inductors are replaced, actually equivalent, to a short circuit. Then we can perform DC analysis of the circuit. Does that make sense? Again, you're looking at an amplifier circuit. Amplifier has both DC as well as AC inputs. So if we wish to analyze, we can do something like a superposition. Not exactly superposition principle, but we analyze both separately, meaning we analyze the circuit just for its DC input, and then we separately analyze it again for AC input. Okay. When we do DC analysis, we replace inductors and capacitors with their equivalents, DC steady state equivalents, which means for a capacitor, it's open circuit. If it's open circuit, RL is disconnected, the source is disconnected. Only thing left in the circuit are the 4 biasing resistors and your DC power supply. And then we can analyze the circuit, which is something that we did previously. Right? When it comes to AC, we follow the same thing, but for AC, it results in a short circuit. And because it results in a short circuit, now you have V1 going into the base. Right? And we replace all capacitors and inductors with their AC equivalents. And the AC equivalents mean capacitor will be a short circuit, inductor will be an open circuit. So we replace inductors and capacitors with AC equivalents. Capacitors are replaced with a short circuit. Inductors are replaced with an open circuit. All DC sources are also replaced. We reduce them to 0. What does it mean to reduce a voltage source to 0? Well, we don't short the voltage source, but we replace it with you're right. Yes, we replace it with a short circuit. How about a current source? Replace with an open circuit. So if you have any sources in there, again, remember, we are only performing an AC analysis. So DC sources must be taken out. All DC sources are replaced. Voltage sources. VTG is my acronym for voltage. So voltage sources replaced with your equivalent of a short circuit. And current sources, CCT, replaced with an open circuit, OC. OC. So knowing these two, if you look at our circuit, we have replaced our DC source with a short circuit. DC source is a short circuit, meaning our collector resistor and our emitter resistors. Sorry, collector resistor is directly connected to ground. Emitter resistor RE is completely bypassed because you have a capacitor in parallel. And VO is directly connected to ground. So there are several things happening here because of the short circuits and the open circuits. Our collector resistor and our load resistor are now in parallel. And R1 and R2 are also now in parallel, which results in this circuit. And in this circuit, you can see collector resistor and output are in parallel. R1 and R2 on this side also in parallel. And thus results in this circuit. So let's take a pause. Write it down, think over it. Let me know if you have any questions. Yes. Because there was a capacitor in parallel with the emitter resistor, the bypass capacitor in the previous slide. And this bypass capacitor is replaced with its AC equivalent, which is meaning it's a short. And because it becomes a short, it takes out RE. So the steps in both are very similar. For DC analysis, we simply replace the inductor and capacitor with its DC equivalents. In AC analysis, we replace it with its AC equivalents. And then we see how the circuit has changed. Okay. Right. And once we have this, we can then choose a small signal model for AC analysis. And since we talk about small signal, let's see what it actually means. Okay. So let's begin with the diode. Right. Our diode voltage VD, DC plus AC. So this is DC, this is AC voltage. Your diode current ID, DC current plus AC current. So total current is VD and ID is listed over there. And we're modeling this as a resistor with resistance RD. Diode resistance RD. Okay. This is again simply the small signal model for a diode. Okay. So we are familiar with the diode characteristic, right? Diode characteristic, and diode turns on around 0.6 or 0.7 volts, call that the turn on voltage. And then if we apply a biasing voltage to the diode, then we are forcing the diode to function at a specific Q point. The Q point is the operating point for that diode. Right? It's the constraints put on the diode by the external circuit. So here is the original Q point right here. And then the AC current ID and the AC voltage VD are small shifts away from the Q point. Okay. So these ID and VD small shifts away from the Q point. The shifts here are exaggerated for effect. They're actually very, very small. Okay. Ohm's law, V equals IR. And so the shift in VD and the shift in ID gives us RD. The resistance at the Q point would be the static resistance for the diode. Delta VD over delta ID, change in voltage with respect to change in current, gives us the dynamic resistance RD for the diode. Okay. And 1 over RD gives us GD, which is, of course, the slope of the characteristics. Okay, slope of the characteristics GD. So diode resistance is RD. I'll write it outside. Diode resistance RD. Conductance is GD. And GD can be given in terms of diode current T plus IS divided by VT, the thermal voltage. And this is true for a forward bias diode. Of course, ID is far, far greater than IS. So we can write approximately GD is equal to ID over VT. Okay. To be considered small signal. Diode voltage, VD, is approximately 5 millivolts. 5 millivolts. The whole point of doing small signal analysis is so we can consider that a nonlinear device is linear over a very small portion. Okay, so it'll exhibit the logic being that the nonlinear device will exhibit linear properties or linear characteristics for a very small portion of the characteristic. Yes. So the question being asked is what does that VD represent? It's the AC. It should be AC. So sorry. Let me make it lowercase v, lowercase t. Yes. Peak to peak value that is being given. Yeah. Approximately equal to 5 millivolts. So if we treat that the input is that small, I mean, if the input is that small, then we can treat it as a kind of a linear device and we can apply linear techniques to that analysis. So all of semiconductor analysis is approximations and assumptions in order to simplify, because no single model can suffice for all environmental conditions or all circuit conditions. Okay, we have to have different models for everything. Just as a example, one of the other classes I'm teaching is 115, which is like circuits and electronics 1 for non-EE majors. And so there they learn about circuits, which is like two terminal devices like resistors, and they also learn about diodes. And so I was talking about a model using constant voltage drop model, CVD model, right? Everybody hopefully recalls CVD models. And so there's an LT-SPICE simulation and there's a theoretical calculation I did. And then I flipped the voltage source circuit containing 3 diodes. And after the quiz, I realized after I simulated that it would work in real life, but it would not work with the CVD model. So like a real life circuit would work, and the circuit that I had designed, but I tried to simulate it with like a CVD model, it wouldn't work. It would just violate KVL. Anyway, so the point being that we always use approximations. Some of these approximations work for some circuits. Some of them are not going to work for other circuits. So in that particular circuit, the approximation of a CVD model would not work. Anyway, let's come back here. So we had the small signal analysis of a diode. Let's look at the small signal analysis for a BJT. What does this remind you of? E212, 2-port networks. Y parameters of a 2-port network. Yeah, like 12 minutes. Yeah, 12 minutes. Let's see, small signal analysis, BJT. Yeah, this is not the hybrid pi model. Hybrid pi model is next. Okay. All right. What do we see here? Output terminals, input terminals. On both sides, we are representing as we're representing it as a current source, right? Output current that is dependent on the input side. Okay. So let's say at the Q point, if I was to write that VCE is equal to 0 at the Q point, and try to determine some of these parameters. Okay. Diode, of course, is just one junction, 2-terminal device. BJT, 2 junctions, 3-terminal device. So we have an input side and the output side. This represents the base emitter input side. And this represents the emitter collector output side. The emitter is common between the two. Okay, the emitter is common between the two. It remains. So from the Y parameters of a 2-port network, I can write equations for IB and for IC. IB can be written as G pi times VBE plus G mu, Greek letter mu, times VCE should be lowercase, because it's all AC analysis, so everything must be lowercase. And then I can write IC as GMVBE. I will explain. I'll write down the expressions just in just a little bit. And GO times VCE. Okay. So in this, well, actually, I'll wait until everybody writes this down. Right? Okay, so what does G stand for? Conductance, right? And you are somewhat familiar with GM, General Motors. Just trying to wake people up, see if anybody's paying attention. Transconductance, right? So all of these values refer to either the input current, input voltage, or output voltage, right? We're simply trying to write an expression for the input current and the output current. So IB and IC, all right? So G pi is a ratio of, or the conductance on the input side. So what is the input current? IB is the input voltage, VBE. So G pi is the ratio of IB to VBE. GM is transconductance. How is the input transferred to the output? So is the ratio of IC to the input voltage VBE. So this is input conductance. This is transconductance. Do you all remember looking up these parameters in the data sheet for the BJT? At least GM. So it's a function of the design and the doping profile from the manufacturer. So it would be listed in the data sheets. Okay. So if you wanted to find the input side, we set the output to 0. That's what we were doing. So when VCE was 0, meaning at the Q point of the transistor, output was 0, output voltage is 0. We're simply trying to find the input. Now, if you want to find the output quantities, which is G mu and GO, we're going to set VBE equal to 0. So if VBE equal to 0, then we can write G mu and GO as IB over VCE and GO as IC over VCE. Okay. Let's see. Okay. I don't think there's time to get into the analysis of a CE amplifier today, but let's see. You can definitely do hybrid pi model. So if you wish to, yeah, go ahead. G mu and GO, that's a good question. Actually, I can't recall. I don't know if there was a name for those specific parameters. The output side. Why am I blanking on this? I'll have to look it up. Okay, to further simplify this, we use what is known as the hybrid pi model. Okay, the hybrid pi model. In there, we are not modeling the input side as a current source. We simply have the diode small signal equivalent, which is RD, the diode resistance RD, and we call it R pi. Okay, this is known as R pi. So you see that right here on the input side. And the output remains the same. We have output resistance, RO, and we have current source GM times VBE. Okay. GM can be given as IC over VT, R pi, beta VT over IC, and RO, output resistance, is the inverse of GO, can be given as VA plus VCE over IC. The early voltage is far larger than VCE, and so we can write this is approximately equal to the early voltage divided by IC. And that's why early voltage is important in the design of systems. This allows us to calculate what the output resistance would be for any given value of IC. Early voltage was something we covered earlier in the class. 5 o'clock in the morning. I'm all about the old dad jokes today. And this was, let's see, what was I going to write here? V is far greater than VCE. Okay. Let's see, 359. Small signal analysis of C amplifier. Okay, definitely don't have time for that one today. Yes, go ahead. Oh, that was just, I mean, just pointing out why it's approximated. Because VA is far larger than VCE. Okay. All right, we'll end class here today. We'll pick up here again on Wednesday with the derivation of a CE amplifier. And we'll see how the gain of an amplifier comes to be.